Okay, good morning. So today we're going to talking about a filter design in practice. The two main topics within today's tutorial will be, first of all, the Windows Sync FIR filter design, and the secondly is bytecode IIR filter design. In the lecture, we talk about there are loads of different ways to design digital filters. There are two big category of digital filter. One is FIR filter, second is IR filter. So in this lab, we're going to select two typical design methods. For FIR filter design, we're going to use Windows Sync filter design, which we covered in the lecture. And for the IR filter design, we were going to concentrate bytecode IR filter design, which we're going to cover this week in the lecture, but we can do the practical stuff first. Okay, let's do a bit of a series start with. So first of all, remind everybody what is FIR filter, what is IR filter, what's the difference? So there are two equations, general equation to representing two structures. So in general, I'm using the difference equation formula here. All right, so you can use Z transform or this kind of signal block diagram to represent digital filters. So digital filter can be represented in different form. So for the difference equation form, the advantage of this form is it directly linked to the programming aspect of that. So easy for us to implement. So for FIR filter, the output signal Yn is equal to a combination of input signal and past input signals with coefficient B in this formula with index K, Bk. That basically means B0, B1, B2 until Bk, depending how large the filter is. So if the filter is 10 order, so the K is equal to 10, basically. So yeah, so that's FIR filter. So the output is only linked to the current input and the previous inputs. So for the IR filter, the general form of difference equation is represented in this formula, and the output signal Yn is equal to a combination of the previous input signal, same term as FIR, plus some other terms of previous output signal, which is buffered and saved for calculate the next output. So the output not only linked to the previous input signal and current input signal, as well as previous output signals. So again, for the coefficient applied to those previous input signals are representing using a variable B. And then the coefficient which applies to the previous output signals, we're using the variable A. So here we have L from 0 to N. So it depends how complicated the filter is. So there can be multiple A's and multiple B's. Okay. Well, one thing I want to mention also, B also refers to a filter kernel if we're representing this as a kind of a graphical representation. Last lecture, I think some of students asked what the filter kernel. Yeah, this domain, they have loads of terminologies. So yeah, we need to familiar with ourselves. So in short, for FIR filter, the design goal is to find the coefficient B. The B is not just one value, it's an array, it's a bunch of numbers to meet specifications, filter design specifications. For IR filter, the design goal is find the coefficient of both B and A to meet specifications. Okay, so that's basically a very concise introduction or brief of filter theory. So let's talk about the second. Let's talk about the practical aspect of filter design. Okay, so what did we talk about the last lecture session? was we using a sync function to design the filter. So those are a couple of diagrams from lecture slides. So the sync function design method is come with inverse FFT of ideal frequency response of ideal filter. Sorry, ideal filter frequency response. The ideal filter is kind of absolutely breakable filter with a cutoff frequency FC. So the ideal filter basically says we have a cutoff frequency here. I want the filter absolutely straight on the pass band and absolutely straight on the stop band. So anything below FC will be totally pass. Anything above FC will totally stopped. So absolutely flat line on the 0 here and absolutely flat line on amplitude 1. So this is called ideal filter. This filter existing on the theoretical world, it cannot be programmed, because to be able to achieve this frequency response, you need infinite length of digital filter. So you need infinite length. So that basically means you need to have infinite length of the sync filter. All right. So I need to get rid of this annotation. Okay, so don't worry too much about the equation here. This is a duration of to implement this. We need infinite long sync filter. In MATLAB, we can simply using a sync function to design a sync filter, and that's basically is going to be the filter kernel B, which is the coefficients of FIR filter. Okay, so you can simply copy paste this example, and from this example you can start with modify that, and also for the formula you can copy paste this formula into MATLAB with sort of like comments. Then I can upload this demo code later on the MATLAB Moodle website. Okay, so this is a formula. So I'm going to just comment out this is a formula, and this is going to be create n, number n is going to create from minus n to n will create probably 2n plus 1. So this will create 2 multiplied by n plus 1 length filter in FIR. All right, so this is basically what happens. So just one line of code, simply you can do it, but we will modify this later slightly to improve this to link to real examples. So first of all, let's try this function, see if it works. So this basically is a simple example. You can use a basic sync function. So then that's it. Then we create a coefficient of B. So this is very, very simple in terms of series. Looks very complicated. So we can simply look at B, say what is B looks like. So use stem B, we can look at what B looks like. So this stem going to draw the output in the discrete format, yeah. So we can actually looking at this in slightly better display, okay. Okay, so you can look at this is a shape of a sync function, yeah. So it's basically like a sine wave and attenuating from fade. You look at a fade in and a fade out sine wave. In the audio terminology, maybe you look at this, a fading sine wave and a fade out sine wave. Yeah, so this is the result. I mean, if you have more samples, it's probably showing a better kind of resolution. All right, so better resolution. So the number of order here is from 0 to 51. So 50 order. So it's because we start minus 25 to plus 25. You have to create this in the symmetrical form, otherwise it wouldn't work. Okay, so then we can say, let's altering a little bit about this. So if I'm going to say, I'm going to want to 50 to 50, would be work. So we can run this code again. So you have more data. You can see you have more data from 0 to 100. Now 101 actually, from 0 to 101. Okay, so that's what. Okay, so this is digital filter, but we don't know the connection between this and your cutoff frequency. So better way I change it to FC, which makes more sense for cutoff frequency. So to be able to make sense of this, we need to actually define some parameters. Okay. For example, we can say how that used in the practical filter design is, say, if we want a low pass filter at certain cutoff frequency. So with sampling frequency, for example, sampling frequency is going to be 10K. Yeah, 10K. And then I want my cutoff frequency of this low pass filter is equal to, because sampling frequency is 10K, half sampling frequency is about 5K. So maybe 400 hertz as cutoff frequency. So the normalized cutoff frequency is going to be FC0, maybe we call normalized cutoff frequency, is equal to 400 divided by Fs divided by 2. So in this case, what we do is say this is sampling frequency, and then this is my cutoff frequency low pass filter cutoff frequency, and this is normalized frequency. Normalized cutoff frequency. So okay, so in that case, then we, instead of I think this is not very good variable because it's got number here, so let's call it FCN, normalized cutoff frequency. So instead of this, we can say what we can run this to have a look what is this normalized frequency will be. So it's basically 0.08 in this case. It's not too, yeah, that's probably right anyway, because it's 400. Yeah, 400 is quite low. So then we can actually put FCN here, and FCN here, FCN, and then you should be able to get the desired filter you want. Okay, so that's your filter kernel in this case. Yeah, filter kernel looks like. And just snap it into here. So when you want to look at, so this is a filter kernel. Basically, each of these point is the B. So I actually plot the B. Stem is one of the alternative plot. So we plot B here. So to be able to look at the frequency response of this is you can use called FV tool, filter visualization toolbox, and you put the coefficients there, B and A. So in FIR filter, because we don't have coefficient A, so A is always equal to 1. We have, but it's always equal to 1, sorry. And the B is the coefficients we're getting from the window sync filter design. All right, so we can look at this filter now here. Go back to MATLAB, FV2, then we say B1, and it should give us the digital filter. It takes a bit of a while because FV2 is quite complicated toolbox. Now we got it. Okay, so now we designed this filter using simple sync function design. All right, so now we can actually evaluate this filter a little bit more, because when we're doing that, FV2, we will not have any information about sampling frequency. So you can see all this value are in normalized frequency. So you can do that by go to analysis and go to sampling frequency and put the actual sampling frequency here. In this case is 10K, yeah, 10,000. All right, so now we can see that's a low pass filter we designed. And then if you look at this axis, it's become frequency kilohertz. So that basically means a real hertz frequency. So then I think somewhere you can actually move in the point somewhere, yeah. So you can see here, the cutoff frequency, we actually say we want 400 hertz. So the 400 hertz is around 0.4. It's about 400 hertz here. So that's this point. Actually, the cutoff frequency should be defined as -3 dB. So you can see the filter roughly aligns the specification we given, okay? But it's not very good in terms of, because this is a start point, the fundamental basics of FIR filter design. So to improve this, you normally using equal rip with iterated process to adding different window to improve that and to minimize order, to minimize excess order. Because what we did is a very basic sync function truncate to have this very accurate cutoff frequency at 400 hertz. You have to have infinite length, but we truncate it, so we create a very closed low pass filter. So this is, we create a filter from manually without using toolbox, yeah? So with your toolbox, you get a better result because those algorithms are more sophisticated. They have quite a lot of optimization going on there, all right? But they all basic start with this point. Okay, so I do have something which you can apply a window here, but I think that's an optional lab because you can then apply a window like a Hunting window or any kind of window size, basically further smooth the fading and fade out curve of this will create a better result. Okay, but that is not the point of today's tutorial. So you can have a look at the optional lab I put up for next week to improve this FIR filter design. Okay, let's come back to the topic. So the most important one is the second exercise. Okay, so now we understand we can design the low pass filter using FIR sync function design. So we're now looking at a typical example of an IIR filter design. Okay. So as I said, the IIR filter design goal is to finding the coefficient B and A. So IIR filter design is very important for audio music processing. That's why I want to concentrate here, because most EQ using IIR filter. It's not going to, FIR filter is good for kind of eliminate certain frequency, whereas IIR filter is sometimes good. It also can be used in limited frequency, but it's also good at smooth different energy of the frequency domain. So for IIR filter design, the goal is to finding both coefficient B and A. So the A is no longer just a 1. So here you got a equation of a typical IIR filter with second order. So not much, not 100 order, but just very small second order filter. So because the numerator and denominator, they all second order filter, so we call it a bichord digital filter. So the goal of this is to find B0, B1, B2, and A0, A1, A2. So they only have 6 coefficients, but it can achieve very good result in terms of for the EQ purpose. So more of the EQ stuff I'm going to talk about next week in the series, but everybody knows EQ because you guys are music engineer and sound engineers. So you probably use this in other domain of the course anyway, but we will look at the theory about that. Okay, so the very famous way how we can get this work is to say, there are loads of methods to do that. The theoretical, in short, basically is the IIR filter can be created from the analog filter prototype. So the analog filter will give you already existing formula to link those coefficients with user specifications, such as Q and the slope and how many dB you want to gain or how many dB you want to cut. So those coefficients has a specific link with those, those user specifications has specific link with those coefficients using a set of formula, There is a DSP guru called Robert Bristol Johnson. I actually met him a few years back when we had a conference on AES. So he actually wrote a very famous book called Cookbook Formula for audio EQ bichord field coefficient. All right. So unfortunately, this link is no longer work in Music DSP. But if you Google search that, w3.org, because it's now become the, so if you look at this here, so this is become the standard EQ for all the web browser, or the W3 is 3W organization to standardize all the web browser, all this kind of stuff, web-based stuff. So all the web-based stuff, if they have audio processing, now this is standard within that. Okay, so it's also put a link here, but unfortunately, I don't know why the Music DSP and put this link down. Again, but this is more permanent link here. So the whole cookbook is not too long. It's quite short. It's full of the formulas, but I think what we're trying to do in the next hour or two is to have a quick look at that. And it gives you basically different type of the filter, different types of filter. You can design low pass filter, high pass filter, low shaving, high shaving, so you got this different filter, LPF, low pass filter, HPF, high pass filter. And it gives the formula between the coefficient, you can see here, coefficient B0, B1, B2, A0, A1, A2. So the actual practical aspect of this is with the knowledge we got from MATLAB and theory. So if you go to online, find this wonderful audio EQ cookbook, can we convert? So this cookbook is programming independent, so you can convert it into any programming language. So we're trying to implement this into a MATLAB. Select one of the digital filter of this to implement in MATLAB, okay? And you can, using FV tool, to plot the curve and to demonstrate if that is the case. Can you really implement this filter with desired parameters? Okay, so that's kind of next 1 hour. So what I'm trying to do here is I'm going to demo my code. At the moment, I'm going to upload this small piece of sync filter design code on MATLAB. And then later on, I'm going to demo my approach to be able to digest this internet source and convert that into a MATLAB code. So that's a very important skill, to be honest, in practical sense in the future, like you're doing project stuff, is to be able to go to internet, find or library. Previously in the past time, now it's more loads of like this textbooks, the internet, and understand it to be able to convert that into your project code, into your project content. Okay, so we will actually look at this in 1 hour time. So I'm going to implement my own and share with everybody around probably 11-ish. Yeah. Okay. So that's so far for today's topic. Again, it's quite. I certainly scratched a bit of content here. So the important bit is have a quick go with my example code of FIR design, and then have look this audio EQ cookbook, see if you can convert this into a MATLAB IR field. All right. So don't be put off by those formulas, and most of formula you can ignore. I'm going to give you some quick hints after an hour time. So 11 o'clock, we're going to go through them, and I will demonstrate how we design specific filter with everybody. So in these tasks, we have a couple of exercises. The focus certainly will be EQ design. So, but we're going to quickly go through some of this FIR design first, because this just same as what we did in the first section, but just using some specific requirements. All right, so let's look at task 1. Design 16-point single function with cut-off frequency at 300 Hertz with sampling frequency is 4,000 Hertz, and plot single function like this, and look at the digital filter like that. Okay, so this is, we already had a result to compare with, so you will know if you're doing correct or not. So quickly, let's go back to MATLAB and try to do this task 1, for example. Task 1, so yeah, the example is certainly what we need to do is just so is quite similar to the exercise we did, but just using different parameter as required. So let's close this figure first. Okay, so if you look at this requirement, so I can copy paste the requirement maybe to the MATLAB, so maybe it's easy to look at. So we want to, first of all, we want to 61-point signal. So when we want 61-point signal, basically the n, basically this means n plus 2, n multiplied by 2 multiplied by n plus 1 is 61. So we can find out n is equal to 61 minus 1 divided by 2. So it's basically 30 point. Yeah. So because this equation, so we can have we know n is, in this case, if you quick evaluate, is basically number 30. Okay, sampling frequency 4,000 Hertz. So we're just changing this to 4,000. Cutoff frequency is 300 Hertz. So we create 300 Hertz. Then need to say the normalized sampling frequency, normalized cutoff frequency is cutoff frequency divided by sampling frequency divided by 2. Then we create B. So this, instead of 50, because we already defined the number of order we need, we're just using n. And then if we want to look exactly as a result, we plot B and look at the filter shape. So we look at this one now. So it will produce exactly result. So the filter shape is this. So if I just give a bit more density to the line, so you can say that's my filter shape, a low pass filter at cutoff frequency 300 Hertz. So to verify this, we can put exact sampling frequency in the analysis window. The tasks 2 and 3 is similar to task 1. We're not going to spend time on that. It's basically a slightly different parameter, and also the window function. I have additional lab I'm going to upload, so you can look at that additional lab sheet. Okay, let's concentrate the task 4. Task 4 is big task. I'm going to implement one of them, one of this low pass, high pass, or band pass filter. So again, I'm going to using low pass filter, but by doing this, you can also doing high pass, band pass filter parallelly. So in later on, what I'm going to do is I'm going to finish everything. I'm going to do a band pass, a low pass filter based on Bristol Johnson's document, band pass, low pass filter EQ. But later on, you can implement that in EQ function. All right, EQ function. So it's probably once you got to the code, it will be easy to convert this to an EQ function. And the key thing of this is I'm going to demonstrate you how to quickly grab the key information from the document, and that helps you to construct some interesting code from any document online, engineering document. Okay, so to do that, I'm going to start with a new script because it's quite a lot of things to do here. So let's do this. So this script is going to be a low pass filter EQ, all right, low pass filter EQ. And this is based on bytecode. Let's go to the website. So if you if you search this book title, you will find this on W3C document. Yeah. So it gives you all the details. What we're going to need from this document is some key elements. And this document actually organized very well in terms of sectioned knowledge about what are the user specifications and what are coefficients. Okay, start with basic. So we all understand the digital filter can be right into different formula. So here it representing digital filter in a Z transform formula. It doesn't matter. We all know Z minus 1, Z minus 2 basically representing the past information. So it's delay information. So all we need to have is to getting the coefficient of B0, B1, B2, and A0, A1, A2. So the good thing about this method is you can actually do a parametric EQ. What I mean is you can actually adjust the establish a directly formula between user input and the coefficients. Hence, imagine if you have knobs and slide, you can actually, design in the MATLAB a parametric EQ in real time, changing the real time. It doesn't need an iterative process to optimize finding any filters. Okay, so if you don't, those couple of lines of this explanation about the theory, we can actually ignore. So start with this point here. So what we it's also talk about fixed point, flow point, architecture stuff. This is quite old information, all right? So not old, this specific talking about hardware implementation. At the time, you might be implement this in a guitar pedal using older 8-bit or 16-bit DSP processor with fixed point accumulator, stuff like that. That's kind of more detail about the implementation. So we don't need to worry at the moment. So let's look at this section. So this section is important because it defines user parameters. The formula Robert Bruce Johnson gave us is very flexible. So it can, so those parameter can be used for different type of filters. I think it totally about probably 6 or 7 different filters: low pass, high pass, band pass, low shelf, high shelf, peaking filter, stuff like that. So first of all, those are the user parameters. Fs is sampling frequency. F0 is center frequency or corner frequency, or shelving middle point frequency. So it depends on the different type of the filter you're using. Okay, so and then also it's using dB again. This is again more audio user friendly, so people would like to use dB as instead of the linear magnitude. So you want the dB or increase or decrease. Q factor, so how sharp the filter is. So probably you guys are also familiar with quality factor. Or bandwidth or slope. So these 3 parameters are redundant. You can use either Q or BW or S, all right? So Q factor. So in this case, we're going to use Q because Q is quality factor. So if you're looking at any kind of a parametric EQ, you probably will find this Q factor. I think the higher Q is the sharpness of the steepness of the curve when you're talking about the transition band or stuff like that. Okay, so in that case, we then can quickly convert that into some MATLAB code first. So we need to have fs sampling frequency. All right, so we can probably just using proper sampling frequency, F0, 2K, yeah, to 1K, maybe 1K is typical within audio band. And then we have dB gain. In loads of cases, dB gain probably is not going to be used in, we call 5 dB. So in this particularly low pass filter case, the dB gain might not be used. Q factor, let's put in number 1 here. I said we got most of them. So we don't use, because you can use Q or BW or S. So we don't use other 3. Okay, here is most important stuff. So the second section of this paper, it talks about some intermediate variables. So this intermediate variable bridges the gap between user-friendly. So this is user-friendly parameters, yeah? All the audio engineer would have sense of this. Whereas intermediate variables are linking between the user parameter into a more computer DSP algorithm-friendly parameters. So, for example, it converts a dB gain into amplification in terms of the linear magnitude. So, first of all, you can say you have amplitude equal to square root of 10 dB gain divided by 20. So in this case, if you're using peaking and shaving filter, using different formula. Okay, so we actually converting dB into amplitude first. So then we have an intermediate variable section. Okay, so we have amplitude equal to, well, square root. I think in my document, I have probably made it easy using computer software programming. So SQRT is a square root. So I have already converted this document into more program-friendly code. So SQRT is built-in function, hopefully. Yeah, let's just double check in terms of it's not right. Not okay. Square root. So we do have this square root of the MATLAB function, so we can directly use that. Okay. So this is amplitude because we are dealing with the dB gain not for peaking and shaving, but low pass filter. Omega, so we also convert cutoff frequency to angular frequency because the formula will accept angular frequency. Okay, so we do a second parameter, which is omega. Omega equal to, I use W stands for omega, but it's actually is Latin omega. So let's close this, make it better display. Okay, omega equal to 2 multiplied by pi multiplied by F0. Okay, F0 already defined, divided by Fs, which is sampling frequency. And in this case, this is grouped together. So make sure we're going to group them together. Although it's probably same result, but just make sure logic is right. Okay, so because we also define Q, which is quality factor, or you can define BW or S, it depends on the user interface you select or you want to implement. So in my case, I want to implement a Q factor, quality factor of the EQ. So I'm going to use this formula here, which is alpha. Actually, it is alpha, but I'm going to using, well, this is a Greek symbol alpha. So I think I also used some symbols, so we can use alpha as alpha equals to using case. I also had this right in the code format in my lab sheets. So alpha is sine omega. Okay, so I use this as omega 0 as well. It thinks it omega 2 multiplied q. Q is equal to 1 here defined. Okay, so that's also done. Alpha. So next step, well, there's nothing. Okay, there's a bit of math about what is Q indeed is, how the Q is related to bandwidth. You know, if it's bandpass filter or peaking or shaving filter, the bandwidth is linked with Q. Finally, we can go to the implementation, or which the exciting bit is we can find the coefficient now. So in this application, they give a set of formula. So those are the sort of like a rule of thumb. So you have a set of different filter. You can say here, okay, the section, if you read the document, is LPF, low pass filter, HPF, high pass filter, BPF, band pass filter, in constant Q, BPF in constant 0 dB peak gain, notch filter, you can notch specific and get rid of one frequency, all pass filter by shaping the face, peaking EQ, which you can actually changing them probably we can search some image about peaking EQ. Yeah, peaking EQ like this. So you can peaking a middle bit of the frequency up and down. Peaking EQ, low shelf filter, high shelf filter. So totally quite a lot. 1, 2, 3, 4, 5, 7, 8, 9, 10 different filters. I remember it's 7, it's more than 7, it's 10 different filters. So what those 10 different filters is, each of the filter, it gives you a set of function or formula, mathematical formula that links user parameter with the coefficients. You can see here, for low pass filter, which I'm going to select the simplest one, you got this B0, B1, B2, and A0, A1, A2. So they got a set of parameter which links to omega 0, alpha. All this one has been linked to intermediate variable, then backlink to the user specification. Okay, let's doing this low pass filter. Again, I have a computer-friendly code converted from this equation in my lab sheets. So if you go back to my lab sheet, it's exactly the same formula, it's just more computer friendly. You can directly copy paste from lab sheets. So the first line of this is a Laplace transform. You can ignore that for a moment. Next Wednesday, I'm going to talk about this a little bit more. So it's really to do with analog filter, because IR filter design is really one of the most popular method is converting analog design filter to digital filter. Okay, so all we need is this bit here, this bit of code. So we want to get a number of B's and number of A's. So let's do this intermediate variable. So here, this section is going to get the coefficients. You can say is you can directly, in the original Rob Johnson's file, it was written in text only. So there's no formula. You can actually direct copy paste from there to any kind of software if you're not using MATLAB. Okay. So you got some warning message because we didn't close each of the formula. So let's just close this formula. So in this case, you should get B0, B1, B2, A0, A1, A2 from the user-defined parameter. Okay, so let's save this for now. This is going to be low pass filter EQ demo. Okay, right. So now I'm going to run this, save any problem of the logic so far. Okay, no error message means good. Let's do a CRC and clear the memory and run again. No problem. Okay. Actually, we already designed a low-pass filter at critical frequency of 1K, but now we need to demonstrate, view the filter, and then we can again apply the filter to the audio signal. Okay, so let's do this quickly. Okay, so let's do this quickly. So what I'm going to do is say, this B and A is individual coefficients. Those are the B's, those are A's. To be able to completely, to use this complete way, you need to collect them. So let's collect this. So B equal to B0, B1, B2. So I collect all three B coefficient into a big coefficient of B. And then I collect A from the same kind of format, A0, A1, A2. I mean, if you are if you're curious about what the actual data is there, you can say here. So any of the, for example, A0 is this number, A1, A2. So they got a set of magic number which does this EQ already. Okay, so what we can do is we can FV2 be A. So we can actually look at the filter using FV2. FV2 is a filter visualization toolbox. So you can supply the coefficient of A and coefficient of B. Oh, certainly B is in front of A always. Okay, so now we can run this and have a look at the filter. So this is my low pass EQ, low pass filter EQ curve. All right. So it's used for the low pass filter in the audio sense. So it's not eliminate, mainly it's kind of a sort of curve is more smooth in more than FIR. You can see there's a bit of bump here. Although it's low pass, it's a bit of bump here. This bump actually created by my Q factor 1. So if I change Q, it will change the sharpness of this shape. Okay, so if I change Q equal to 0.5 and run this again, it will be different. You can see that's 0.5. Now it's very smooth without any bump. So the Q actually controls the property of this curve. All right, so the higher Q, I mean, especially in the peaking filter later, if you implement it yourself, the higher Q will have a kind of a more sharpness. So this is lower Q, so the curve is basically more smooth, whereas the higher Q has a bit of sharpness than this. So, so you can actually adjust it. For example, now I'm going to say I want 4K as cutoff frequency. You can adjust those user parameter. So let's put this section as user inputs parameters. All right, and that will reflect into the data. So this now is basically try to cut at a 4K rather than 1K. So the curve is pushed backwards a little bit more. Having said that, this is more EQ curve rather than the FIR filter. So those cutoff frequencies are not very obvious, but the curve actually changes when you change the parameter. It's more of the to colorize the audio. You guys more better than me, but how this curve affects the audio, affect your music, that's another kind of topic than this. Okay, so we can show that again. Then the way also we can trying to testing it is you can actually run this through some noise signal. We can actually test to see if it works. Okay, so let's have a quick go on that. So normally we can create a random noise. So we can say random and so test sig, we just create any name, test sig equal to random and 1 fs. Let's create 1 second of random signal with sampling frequency because that's basically is here. So let's try that and then say normalize it. Test signal equal to test sig dot divided by max bracket ABS bracket, and I think RPF EQ. All right, and then we can so test null is looks like we can plot it. So it's here text null. We can plot them. So this is a random noise signal. I was going to play it, so make sure you got earphone volume down a bit. So I'm going to play that sound, so we can now test. Play this is plays the original noise signal. Okay, so I'm going to make the sound. Oh, sorry, we need to with sampling frequency as well. Okay, so let's play that. We got some noise signal, yeah, about 1 second. So now we're going to apply the filter. Okay, so remember there are a couple of comments you need to remember. So when we apply filter, you can say, let's give a name called filtered sig equal to a function called filter, which is MATLAB, which does the filtering process. So when you do a filter, so what you need to do is give 3 parameter, yeah. BAX, BA is your basically your representing your filter. In this case, my low pass EQ, and X is my test signal. So okay, so we already got B and A, so which is nice. We just use the standard variables B, A, and we use the test signal is going to be, we filter this out. Okay, so let's try that. Okay, we should be able to get to filter sig. Then we can do a sound again. Create a filter, or we create a filter here already, and then we apply the filter to a test signal, which is random noise, normalized, and then we say if the filter has been filtered somehow colorized. I hope it works. Just try again. Original noise, then after filter. So it does colorize the noise in terms of, you know, a low pass kind of effects. Because the EQ is not eliminated any high, all the high pass, it just like attenuate the high pass more, a high frequency signal more. And this is interesting way because you now can changing on flying. So you basically changing anything here, you can change in Q, changing one, and it will give a different EQ. So if you imagine you had a loop, so you basically create interactive parametric EQ, and you can create a multiple of this. You can do 3-band, 4-band EQ, you know, with low pass, shaving, high shaving filter, and high pass filter, stuff like that. Okay, so that is basically the task of that. I think one thing I was a joke about this for my previous student is the key element of this lab is to learn how to copy paste, isn't it? So you copy paste the existing knowledge online. I mean, to say that is a bit mean, but basically is you don't reinvent wheels. Some DSP guru create this, but for most of our current engineering work is to be able to understand what does it mean and can we convert into a viable product, or can we then do improvement based on that? Okay, so I just did one of these example, but some other filter may be more interesting to you, like a peaking filter, low share filter, or notch filter. Okay, so if you're really interested in EQ, you can try to experiment most other filters as well and apply it to real music if you want to see adjustment. Certainly, it's more kind of in terms of usability, it certainly is less convenient than DAW, but the way is to study the internal structure of DSP. Yeah, so if you're doing production, certainly just use DAW, but then now we can create our own EQ. You know, you can actually write your own plugin on this. You can write your own software, EQ software based on this arguments.